improving RV precision.
All right, thanks everyone. Our goal is to, of course, looking through the iodine cell, which is over here. You can tell by its pinkish thing, but you can't see it probably. And to find Earth 2.0 eventually. And for that, we need to really push the radial velocity procedure. And just to demonstrate how hard it is to detect Earth, this is the radial velocity curve of the Kepler 78 system. And you can see there is quite a lot of RV scatter. The data are taken by the high-res spectrograph. In fact, the planet RV amplitude is only 1.7 meters per second, while the unexplained scatter, which we dubbed as jitter, is about 2.1 meters per second. So to really push the limit and try to reach planets that are more and more like our Earth, we really need to beat the jitter. And to clarify here, my work here mostly deal with the instrumental effects that contribute to the jitter instead of the stellar activity, which is actually hotter. And before we move on, let's take a brief review of how the iodine technique works to search for planets using radial velocity measurements. Our goal is to model the observed spectrum, which is represented by the black dots here, which consists of the stellar spectrum in black and the iodine lines in green broadened by our spectrograph. And we take the models, the reference spectra, which we actually derived empirically and taken them as the ground truth, and we shift the stellar spectrum by the guessed amount of radial velocity shift, multiply it to spectrum, and convolve it with the spectrograph PSF, and try to match the observed spectrum. We iterate until we get the best RV fit. So as you can see, there are gazillion things that can go wrong in this process, right? And to diagnose what are contributing to the jitter term, one common practice is to analyze the radial velocity of a RV standard star, which means that we think the RV scatter of the star is very close to 0. And this is a particular star observed by Spectral in almost 10 years span. And the internal error for this star, which is almost the photon limiter error, is about 1 meter per second, while the actual RMS is 2.6 meters per second. As you can see, there are a lot of unexplained scatter over here. This star is actually a little bit magnetically active. And if you can pick up the radial velocity for each season, you can see there is some sort of persisting pattern if you plot it as function of months of year. And to help us diagnose what the problem could be even further, we can plot instead in axis the barycentric correctional velocity of the Earth, which is the Earth's relative motion to the Sun projected to the direction of the star. Here is the barycentric correction. As you can see, there is a strong correlation between barycentric correction velocity and the radial velocity. So there is definitely something earthly over here that gives you this aliasing signal with a period of 0 years. And ironically, it turns out to be the Earth. It's the Earth's atmospheric absorption. It's the telluric lines that gives you this aliasing signal, pulling the stellar lines and the iodine lines that gives you a slightly wrong radial velocity. And there are a lot of strong water lines, in fact, in this wavelength range. We work with the iodine technique. And for the strong lines, you can just simply masking them out throughout the spectral region. But in fact, if you just zoom in, you can see almost an infinite amount of lines, which the atmospheric expert calls the grass. They're just everywhere. There's no way to mask them out. You're going to throw out 90% of your spectral domain, and you can't do any precise radial velocity. So the way to go is to model them. And I'm going to skip a million slides that detail all the challenges and complications of modeling the telluric lines and give you the results. This is the RMS before the correction. You can see this signal, and the RMS is about 2.6 meters per second. This is after it drops to 2.4 meters per second. And the difference is what is striking over here. You can see the RMS is 1.3 meters per second with a larger amplitude. This is your radial velocity procedure floor or ceiling that you will hit if you don't take care of the telluric lines. You can't get past 1 meter per second in the optical if you just ignore the telluric lines. So to really take care of this, you need a lot of modeling, careful modeling. And it's just a note quickly. This doesn't only affect the iodine technique. It also affects the therm-argon calibrated precise RV. This is from 2 papers from the Hobbs team. Currently, the Hobbs pipeline, they mask out the strong lines, but they do nothing about the microtelluric lines. Those 2 papers address the tiny microtelluric lines, and this is the impact of the telluric lines with the function of various intercorrection for various types of stars. As you can see, for certain M stars, it can be as large as 1 meter per second. And the only way really to take them out with this cross-correlation technique for precise RV is actually modeling. So you have to add modeling to part of your pipeline, and this is another paper. This is precision before and after modeling the telluric lines, microtelluric lines. All right, to switch gear a little bit and talk about the other thing that can go wrong in this whole forward modeling process. We look at the green, sharp, high resolution, high signal noise reference spectra of the iodine lines, which traditionally, now I'm going to switch instrument and talk about the Hubble telescope and its high resolution spectrograph, which is fiber fed and temperature stabilized, but it has a really velocity precision of 3 to 5 meters per second. Well, it should be capable of doing 1 meter per second. So the problem we suspect with this, we suspect some problem with the iodine reference spectrum here. Traditionally, a iodine reference spectrum is taken by a Fourier transform spectrograph, or FTS, that has a scan using this essentially a microsync interferometer. It provides high resolution, high signal noise spectrum that is just marvelous, resolution 500,000 and all. But we actually took a new FTS scan for the HET iodine cell in 2011 and compared it with the old one scanned almost 20 years ago at KPNO, and as you can see, the two have substantial differences in terms of wavelength solution, line depth, and even line depth ratio, which is even worse. So what can go wrong? So the difference can be either real or unreal. Both are concerning. If it's real, which means the FTS scans capture the real cell properties, this means we have a changing iodine cell. If I have a changing calibrator, that's really bad. If this is unreal, this is also bad because this put into question the quality of any FTS scan. Which one do you trust? It's pretty hard to tell, right? So to break the tie, we jump out of the Fourier space and step into the real space and use a Echelle spectrograph instead of Fourier spectrograph to break the tie between the two. And we found the almost perfect spectrograph for the task of validating FTS scans for iodine cells. It's called tall spectrograph. It has a resolving power of 500,000 using its TS12 setting. It's in the clear room of McDonald 2.7 telescope. The downside of it is you can only take 2 angstrom per frame, and you can take 30 to 60 angstrom per day if you're fast and if you don't have bathroom breaks and lunch breaks. The reason is this. This is a cross disperser for the spectrograph. To change the angle of the cross disperser to move further in the wavelength space, you have to go into the basement, grab this bolt over here, and tap on this spinning wheel and hope the veneer caliber will just move in the right amount of angle so you can move forward in the wavelength space. But nonetheless, this thing is marvelous. It delivers what we wanted to deliver. This is a comparison of the shell spectrum for the HET iodine cell in black, and it's a new FTS scan in red, and the old FTS scan almost taken 20 years ago in green. As you can see, the new scan agrees with the shell spectrum, which really indicates a probable changing cell. So we're in the process of further characterizing the cell property and see using a theoretical code to predict the iodine lines to see if we can fit cell properties such as temperature and column density so that we can achieve higher radio velocity precision, have a better reference spectra for our calibrator. So what's the future? Where the future lies? I really believe that we need a modern code for extracting radio velocities from data, either iodine data or the thermal argon calibrated, or in the future the laser cone or some sort of cone calibrated data. And I'm in the process of writing a new RV code that's in Python, and it will be available publicly on GitHub. So I invite everyone who's interested to join the collaboration. It has a Bayesian option, although you can choose your traditional maximum likelihood. And it's highly modular and flexible. You can use it on any telescope. You just plug in the modules and plug in any of your favorite model components, and it will go. This is the first results from the code. It's a analysis plot for a spectrotron. The triangle plot from the MC patent by Funamani et al. 2013. And as you can see, we have almost 15 or 16 parameters in the forward modeling process. And the most crucial one is the radial velocity. And it doesn't really have any strong covariance with any of the parameters. The W indicates 2 of the wavelength solution parameters. All the rest parameters are IP parameters. So this really gives us idea. We have a terrible, sorry, IP means the spectral PSF. We have a terrible spectral PSF model. And this is for the first time it's been numerically characterized. And in the future, we're going to improve a lot of things. And we're going to incorporate Gaussian processes as used in Starfish, written by Ian Chikala. That's all. Thank you.
So after the drag for the telluric line in the visible band, in optical wavelength, you get to a precision or RMS 1.27 meters per second.
No, that's the one I removed. We get down for a particular standard star, we get to from 2.6 to 2.4.
Okay, that's in the optical wavelength.
Yes.
And in the near infrared, the telluric line contamination will be more severe.
That's right.
And how can you comment? How do you address like telluric line contamination? How do you remove them and then get to the 1 meter per second with HPF?
That's a good question. I'm actually not part of the HPF team, but I think we did talk about this issue. I think the solution is still in modeling. So I believe that's also currently what the precise RV experts in the near infrared are already doing. They do model the telluric lines in the infrared. In fact, many of them use the telluric lines as their wavelengths and velocity calibrators. So it's the same principle. You fit for the column density of the molecule species, and you fold in telluric spectra as part of your model. Is that what you're asking?
Yeah, just want to hear from your opinion.
Oh, okay. Well, if you want my opinion, I have a lot of faith in modeling telluric lines, and I believe for future spectrographs, like the ones people might be using for wind, which spans both optical and infrared, I believe we will be able to beat the aliasing signal caused by telluric lines by just modeling the lines. I believe we can do, we can eliminate, and the leftover residue RMS caused by microtelluric lines can be beaten down to below 20 centimeters per second or even better.
You can do the same thing now.
Yeah, I think so. It's stronger, but we really do understand telluric lines pretty well, in my opinion. Although the hydra team might disagree, but I think we can model them pretty well.
How much do uncertainties in the high-trend database affect your results?
Sorry, can you say?
How much does uncertainties in the high-trend database in terms of line positions and line strengths?
Oh, that's a good question. I'm not sure. I think, but I do know by talking to the hydra team, the uncertainty is small enough for our purposes. It might sound scary. For example, most of the lines that doing this aliasing effect come from the water lines, right? But the water comes from lower atmosphere, and it is affected by wind. So your water lines are actually not stable to 2 meters per second precision. But you're not measuring the water line velocity to 2 meters per second precision. You just remove the Doppler power brought in by the water lines as much as possible, and you really don't care to that precision. So that's okay. So the tiny, well, in my opinion, tiny uncertainties in the high-trend database in the optical wavelengths is actually even smaller than that. It's even smaller than that.
All right, let's thank Sharon again.